Hello everyone, myself Dinesh. Today we are going to discuss about our team's mini project which we have done during 3rd BTech second semester under the guidance of Dr. V. Akila. Our project is a streetlight management system using solar panels. Coming to the abstract, the smart streetlight project aims to improve the energy efficiency and the urban safety by using sensor-acquired streetlights. This can be automatically adjust the brightness based on the ambient light levels and the presence of pedestrians and vehicles. The project incorporates a central management system implemented by using the ESP32 module and Bing IoT tool. The implementation of this technology can lead to a significant cost savings, improve security for the cities, and raise the overall quality of life for residents. Vehicle detection system is implemented to control the street lights when vehicle is detected. LED does not consume large amount of electricity. By the combination of both LEDs and LDRs, the intensity of light can be controlled and save more electricity. To make step towards a clean energy, solar panels are used to power the street lights. So existing systems. So most of the existing systems are powered by conventional energy, which increase the carbon footprint. This system even using LDR sensors to control the intensity of the street light according to the ambient light conditions. IR sensors utilized on one roadside send signals for the LEDs to get glowing for the next specific section of the road after sensing the density and movement of the vehicles. Our proposal: there are many smart street light systems which are powered by conventional energy. Now we are extending it by adding solar panels. The use of solar power eliminates the need of conventional power source, reducing carbon footprint and operating costs of the lighting system. The solar energy is stored in lithium-ion battery and used to supply the power. The lights are equipped with sensors that they detect motion and again adjust the brightness accordingly, reducing the energy consumption. Raghu will continue the next part.
Now I'm going to deal with UML diagrams. UML diagrams represent various states in which the system is going to be when it is in working mode. There are various UML diagrams which are in use. The first one is activity diagram, and second one is data flow diagram. Third one is sequence diagram. And now first we are going to discuss about the activity diagram. In activity diagram, first we initialize the system, then LDR uh, tries to detect the intensity of the light. If the intensity of the light detected by the LDR is less than 25%, then the microcontroller will switch on all the lights connected to it with minimum intensity. Simultaneously, it checks if there are any faulty streetlights connected to it. If there are any faulty streetlight connected to it, then it will send an appropriate message to the app. If no, it waits for IR sensor input. If the IR sensor input is high, that is vehicle is detected on the road, then the street lights are turned on to the maximum intensity. If the IR sensor in output is low, that is the vehicle is not present on the road, then the street lights continue to glow with the minimum intensity. Simultaneously, the microcontroller will send the real-time data sensed by the sensors to the app, and the appropriate state of the proposed system is displayed on the app. If the intensity of the light is greater than 25%, the streetlights will be in the off mode and the battery will charge if it is not fully charged. And next comes the state chart diagram. State chart diagram depicts various states that system undergo when it is in the working mode. Firstly, this in the system, the streetlights are in off mode and the system waits for the input of the LDR sensor. If the LDR sensor input is low, then the system change its states to the street. Then system will change its state where the intensity of the light is minimum and it simultaneously waits for the IR sensor input. If the IR sensor input is high, that is a vehicle is detected, then the system will change its state to where the streetlights are glowing with the maximum intensity. If not, the streetlights continue to glow with minimum intensity. If the LDR input is high, that is the intensity of the light is more, then the system will be in the state with the battery recharges, and then simultaneously the microcontroller will send the data to the cloud. Here comes the sequence diagram. Sequence diagram depicts how the communication between the entities inside the system or proposed system is done. There are almost seven objects. First one is vehicle, second one is sensor, Third one is microcontroller. Fourth one is street light. Fifth one is battery. Sixth one is cloud. And seventh one is mobile app. Firstly, when vehicle approaches the system, the sensor sends to the microcontroller a message that vehicle is on the road, and the microcontroller replies back with a message: is there enough lighting conditions? If this sensor's reply is no to the previous message, then the microcontroller switches on the next four streetlights with the maximum intensity. If the sensor's reply is yes, then the microcontroller switches on or recharges the battery to the maximum level if it is not at maximum level, and simultaneously the sensor's data is sent to the cloud. Then the data which is sent to the cloud is retrieved by the app, and the appropriate state of the system is displayed on the app. Here ends the sequence diagram and the data flow diagram. Data flow diagram depicts various ways in which the data is flowed inside the proposed system or the system architecture. Firstly, the vehicle when the vehicle approaches the proposed system, a real-time data sensing is done by the microcontroller and the sensors attached to it. Then, two processes are done by the microcontroller. One, it switches on the street lights if necessary, and it also sends the alert messages in specific conditions. And this real-time data, which is sensed by the sensor, is transferred to the database. And from the database, the data is retrieved on the mobile app, and the appropriate system state is shown to it. Vasu will continue.
Methodology. In this project, we use ESP32 as our microcontroller, which enable us to transmit the data from the sensor to the cloud. We connect sensors like LDR sensor, IR sensor, voltage sensor, current sensor to the circuit. In this method, we switch on the street lights whenever the sunlight is below some threshold. And if there is no obstacle detected during the night time, the intensity of the street light will be brought down to 40% of its full capacity. If an obstacle is detected near any street light, the next 4 to 5 street lights will be glow at 100% of the intensity. The system will be even detect the fault street lights when the help of current and voltage sensors. Results. This image shows that whenever there are low lighting conditions and no vehicles detected, the street light LDRs will glow minimum intensity. This image shows that when the vehicle is on the road, that is when the IR sensor detects the object, then street lights glow with the maximum intensity. Results. These three images shows the various notifications when system is not functioning properly. It shows two notifications when the street light LES does not function properly, and another is sent when the solar panel is not working properly. Conclusion. Renewable electricity. Solar panels offer a clean, sustainable source of electricity that helps reduce dependency on fossil fuels and promotes a better environment. In reducing carbon emissions and addressing climate change, the project helps. Cost saving. Solar powered smart street system can drastically lower government's energy bills. The abundance of sunshine assures a steady supply of electricity, decreasing the demand for grid based electricity and ultimately lowering operating costs. Energy efficiency. To maximize energy efficiency, integrate smart technology like LED lighting, motion detection, and adaptive controls. In order to save even more energy, streetlights can alter their brightness in response to the amount of ambient light and the presence of people. Increased safety and security. By providing well lit and uniformly illuminated public spaces, smart street system increase safety by improving visibility for drivers, bikers, and pedestrians. Security measures may be further improved by integration with surveillance cameras and emergency warning systems. In this project, software and hardware requirements are IR sensor, LDR sensor, voltage sensor, LED, ESP32, and jumper wires and power supplies. The softwares we are using Arduino IDE and Blink Cloud and Blink app. Thank you.